Okay, so hi everybody. Can you hear me? Probably. I hope so. It's a great pleasure to introduce a colleague and a friend, Andrei Gruzinov. Andrei is originally a plasma physicist. I used to work on hardcore plasma physics and tokamaks, but has since migrated to astrophysics in late 90s and has done many really interesting things in astrophysics. He's one of the co-inventors, for example, of fuzzy dark matter that many of you know, even though he's more skeptical about it than most people. He's done some fundamental work on the theory of MHD turbulence and gamma ray bursts and pulsars. But today he's going to talk about something completely different, which is the dynamics of clusters near black holes.
So I want to tell you about statistical mechanics of stellar clusters. And the interesting thing will be that it will be a non-Gibbsian statistical mechanics, and also it will be non-Gibbsian statistical mechanics of systems which really exists. Some mathematicians and some perverts talked about non-Gibbsian statistical mechanics, but in real life, as all of you of course know, a system in statistical equilibrium will be perfectly Gibbsian. That is to say, you just compute the statistical sum, and you do it for water, for vapor, for Ising model, for anything, and it just works. This work is based on a recent paper with Yuri Levin and with Jiarong Zhu, who is a graduate student at NYU. We need to have some plan. So the first thing I wanted to tell you about is what is this real life problems that this statistical mechanics solves. Then I will tell you, and this real life problems that it solves is why this problem is interesting according to Levin. The problem is interesting to me for a totally different reason, which I will explain to you. Namely, I believe that this non-Gibbsian character and the very fact that statistical mechanics can be used to describe clusters of stars is, at least in my eyes, way more interesting than the fact that it describes real systems. Then I will tell you what we have done in this paper, and then I will tell you about this non-Gibbsian stuff, the most interesting thing. According to me, this non-Gibbsian stuff poses, I think, a very interesting challenge for, I would say, for theoretical physics. I even contacted some well-known statistical mechanics people, and nobody was able to help me with this non-Gibbsian problem. They don't know what to do in this situation. So we shall see. Maybe we will make progress in this 150-year-old problem. 150-year-old meaning Gibbs and Boltzmann apparently solved this problem, but maybe not fully. Maybe there are these somewhat exotic, but nevertheless real-world systems which are described by non-Gibbsian statistics. So let me start with these real-life problems. So what are those real-life problems? The most famous one associated with the statistical mechanics of stars is the so-called Tremaine disk. As far as I know, this is official terminology, Tremaine disk. So this is about the cluster of stars, the so-called blue cluster, which was found around the nucleus of M31. So if you take an HST image of M31, a square 3 arcseconds by 3 arcseconds, which corresponds to about 10 parsecs in Andromeda, then you will see this funny distribution of stars here when there is this bright nucleus, but then there is a second nucleus. And there is some fuzz of an overall spherical, elliptical shape. And this distance is our water, like 2 parsecs or something. So there are some blue stars over here. So it is this double nucleus in M31, which people call the Tremaine disk, or also blue cluster, because apparently these stars, which are concentrated off the supermassive black hole in M31, these stars are all bluish, if I remember correctly, like 100 or 200 million years old stars. Tremaine identified this thing as stars in elliptical orbits. And also the same Tremaine with tumor, mostly with tumor, and for that reason we will call it TT thermodynamics. The same Tremaine said that perhaps these funny elliptical orbits can be describable as a statistical equilibrium system. So they literally use Boltzmann distribution to calculate this funny lopsided system. They call it phase transition. And so this, they wrote a whole series of papers where they identify phase transitions in thermodynamic equilibrium. And however, the full solution of this problem, I think it is fair to say, the full solution of this problem was only delivered in our paper because this thing is very likely rotating, which requires a second temperature, and only with, in this paper with Yuri and Jiarong, we introduced the second temperature and solved the problem in its full generality. And so our next plan will be, in fact, not to just point at this picture and say, look, lopsided, but rather to really identify the thermodynamic equilibrium, which would be consistent with the observed morphology. And I would assume, to show you the level of my ignorance here, I don't even know, do they have velocities here? So then our task will be not only reproduce the morphology, but also the velocities of stars, and to show that this is thermodynamic equilibrium up there in the sky. Another thing which interests my co-author is that the same thermodynamics tells us about segregation for stellar mass black holes. Whatever, 30 solar masses black holes. It turns out that under the same thermodynamic equilibrium assumption, we can calculate how stars of different masses will be distributed. And in a cluster like this, for example, the prediction would be that these stars heavier than the usual star, the heavy stars, but our main interest is this stellar mass black holes. They will be in a very elliptical orbits. And if I understand my co-author correctly, he says this is interesting because high eccentricity in spirals are good for gravitational waves and stuff like that. Another thing, again, I'm just I want to get rid of this annoying astrophysical phenomenology before jumping to interesting stuff. So that's why I'm blaming everything on Yuri. So another thing that Yuri finds interesting is that perhaps elliptical disks of fluids, not of stars, in those funny potentials can also exist. There is some theoretically interesting thing about this. Think about it. Why consider thin cold disk? Why thin cold disks are circles? That's because if you have a cold disk, then in a cold disk, of course, there is no pressure, right? Zero temperature, zero pressure. Without pressure, a fluid particle goes just like a collisionless particle. So a cold disk there, by necessity, consists of orbits which do not self-intersect. And so a one-parametric family of orbits, namely circles, don't self-intersect. But so do all these ellipses. Right? I can consider one-parametric family of ellipses with fixed eccentricity, but with growing semi-major axis. This family will be a family of non-self-intersecting curves. So why the hell don't we see elliptical disks? Or at least we don't see them.
Doesn't that give you a density gradient? It gives you a pressure gradient.
No pressure, cold disk. That's what I started with. Right, cold, absolutely cold disk. If it is cold, what's the problem?
Well, if it's zero temperature disk.
Yes, it's a zero temperature disk, indeed. And so, but at any rate,
the difference between a zero temperature fluid and free particles.
They cannot collide. That's all there is. Right? They don't collide. Here they don't collide. So it is a solution of zero temperature hydrodynamics, no problem. Of course, this looks weird, but anyway, I don't need to explain it. He believes that maybe such disks, in principle, can be powered by these stars. So this is just a list of real-life problems which this thermodynamics addresses, and this exhausts my knowledge of this phenomenology. Now let me tell you about what interests me. As Yuri correctly said, I come from plasma physics and from nuclear physics. And in this, especially in plasma physics, of course, but also in nuclear physics, we know and value statistical mechanics, right? Because we are dealing with quasi-thermal systems often. So question. So once you come into astrophysics, being a plasma physicist, and once you see the globular cluster, your first impulse, obviously, is to, is there a clock here so I can keep track of time? No? No clocks? Okay, can you warn me 15 minutes before the end? So if you see a globular cluster, just some 10 to 5 stars or something, and if you know nothing, then your first impulse is to apply Boltzmann distribution or Gibbs distribution to this system. So why don't you consider this is a perfect system? Stars have very small sizes. They rarely collide. So those are point masses. I know that they move according to Lagrangian equations of motion, where my Lagrangian is kinetic minus potential. And I also know that instead of solving these equations when I have a lot of stars, I can instead just take the energy and get my distribution as, so the probability to be in phase space point gamma will be just given to the inverse statistical sum. And by the energy of this point, so gamma is a point in phase the point is in phase space, right? So gamma lists all radii and all velocity. So given the point in phase space, I can calculate total energy. Knowing total energy and the statistical sum, where beta is the inverse temperature. So knowing the statistical sum, I can predict the probability for my system to be in a certain point in phase space. This is standard statistical mechanics, which always, always, always works if your system is in thermodynamic equilibrium. Okay? Wonderful. So why don't we apply statistical mechanics to globular clusters and classify globular clusters according to their temperatures or something? So before I give you the answer, I want you to be honest with you. Do you know it or don't you? Don't tell me. Just, oh, do you know the answer? Tell us.
Negative specific heat.
Negative specific heat is one thing, but so what? What exactly will happen when I will compute this statistical sum?
Well, the equilibrium is a tightly bound binary and everything else at infinity.
Can you be specific and answer my mathematical question? What will be the value? What exactly will go wrong as what you say is physically correct? So what David is speaking through his mask, probably you didn't hear him, but
Infinity.
Right, but you are a co-author, so you should have kept your mouth shut. Exactly, statistical sum will diverge, but David said this absolutely right. So it's nice to be talking to people who know. Physics-wise, and this of course should be common knowledge in astrophysics. Physics-wise, what will happen is that you will form tight binaries and evaporate the entire thing. So there will be formation of tight binaries and evaporation of the entire thing, but mathematically it manifests in the fact that the statistical sum will just diverge. Divergent statistical sum signals this problem. And of course it is correctly caught by Boltzmann or by Gibbs. Really, I use them interchangeably. It's the same, E2 minus beta E. So whenever I say Boltzmann, you should replace him by Gibbs. We are patriots, after all.
Gibbs was in some ways one of the first great American physicists.
Yes, exactly. And he, in fact, did exactly this, because I am using really the full statistical sum, not just Boltzmann distribution of molecules with height, okay? So I am using really Gibbs. So to understand this thing, this is what's really interesting here. To understand this thing, consider a stupid statistical mechanics system consisting of just two particles. It's okay. You can apply statistics to whatever. It will not work for two particles, but you will see the origin of the problem. So for two particles, I can always replace it with one particle in the, with reduced mass and stuff like that. So it's just motion in a central potential well. Then, you see, my statistical sum will be integral d3r because kinetic energy, because come on, man. Because gravitational potential energy is negative, so E2 minus beta is this. Now look at this. At small radii, this guy here is r cubed. This guy here is 1 over r. At small r, this is algebraically small, but this guy is exponentially large. So statistical sum will diverge at small radii, and physics-wise, this is exactly what the story we have heard. You will start forming tight binaries, and at the expense of tight binaries, you will fly away. So this, right. For negative beta, it will not work either. Because for negative beta, you go to infinity. Right. So now question. So when I understood this, I said the following incorrect thing. I said, oh, maybe this is because this Gibbs thing where you can introduce the exponential simply does not work for one of our diverging potentials. And I said that maybe I should go back to the basics and consider the so-called microcanonical distribution, because really, remember where the statistical mechanics is coming from originally. You are just, of course, saying that your system distributes itself uniformly on the constant energy hypersurface, right? Because energy is conserved, you go everywhere you can go without violating energy, constant energy. So constant energy is some hypersurface in phase space. You travel into each corner of this hypersurface uniformly. So I thought that maybe all I need to do in this system is to take, let's say, system. I have normalized everything. Kinetic energy, potential energy, negative total energy. And then it's easy to see that the resulting thing will indeed converge. Because if I go to small distances, at small distances, my phase space to go to small distances is R cubed, configuration space. But my energy here is only 1 over square root, right? And so at small distances, it's okay. Now, to my shame, it took Tremaine to point out that this does not work either, because once I replace 2 particles with 3 particles, or any n greater or equal than 3, then in fact microcanonical will diverge here too. And of course, for the same reason that we have already discussed, right? If you have you cannot argue with this physics mechanism. You form binaries, you give energy to other stars, and it's easy to see, right? If you have n stars, then what you should do, as was pointed out by Tremaine, for some reason I didn't realize it myself, even though it's very simple. What he says is take 2 stars, put these 2 stars very close to each other. For that, there will be a phase space penalty R cubed, right? Because the probability to be within R is algebraically small. However, once you have paid the penalty for putting these 2 stars close at R cubed, the other n minus 2 stars now lie on a sphere of radius V. Come on, man. Okay, R cubed. Huh? You can finish this exercise on your own. The point is that physics is still with us. You form tight binaries and scatter other stars. So why am I talking about this? Because you see, this is an example of a system where statistical mechanics doesn't apply. So there do exist systems which are not describable by statistical mechanics. Statistical description simply fails because, as correctly pointed out, it doesn't exist. And that's why people like Piet Hat build special purpose machines, right, which do, so you have to do dynamics somehow. And that's why this Tremaine thing was so interesting to me, because Tremaine thing, I should really say, this is an example of money to the money. I should really say TT thing, Tuma-Tremaine thing, okay? So that's why this Tuma-Tremaine thing is so interesting to me. Why their thermodynamics works. That's why. You have a star cluster around a black hole. And you are only working in the situation where the mass of the black hole is much larger than the mass of the cluster. I spent this entire morning trying to find out what is the mass of the blue cluster in Andromeda. I failed. I know that the mass of the black hole is 10 to the power 8. I think it is we are pretty sure that the star cluster there is like 10 to 5 or something, probably 10 to 6 stars, I think. But anyway, theory-wise, we are working with star clusters which are much less massive than the black hole. Then, if this is my black hole, and this is my star in some general elliptical orbit, then to the first approximation, I just have this ellipse. And so what Tuma and Tremaine are doing, they are doing thermodynamics not of point masses, but of Keplerian ellipses. So you spread the mass of a star over this ellipse, and then you consider interacting ellipses. As these ellipses interact, they will move each other around, and for reasons I will not go into, everything will change except the semi-major axis. So you can change eccentricity, you can change all orientations, but you preserve this. Okay, reasons are simple, because semi-major axis is the adiabatic invariant. Why? Because adiabatic invariant is energy over frequency, and energy depends only on semi-major axis, and frequency also depends only on semi-major axis. Therefore, energy over frequency, which is the adiabatic invariant, is in one-to-one correspondence with semi-major axis. So these little ellipses will move around, changing everything but semi-major axis. Voila. We have statistical mechanics, but with a very funny phase space, because the energy of the star does not change. Semi-major axis is fixed. Potential energy of the interaction of the star with the black hole does not change. It is fixed. Only those ellipses are influencing each other, changing their orientations and eccentricities. Detailed balance, the only thing I can say, detailed balance is a derived concept. The primary concept for me is that this, after you fix the semi-major axis, the remaining dynamics is Hamiltonian. So you have a pure Hamiltonian dynamics, and therefore, in equilibrium, you will have this detailed balance, but you don't need to know anything about the system, but just knowing that it is a Hamiltonian system. Right, it is a purely Hamiltonian system.
Even if I didn't know it was Hamiltonian, if I knew I had detailed balance or something, you can start that.
Then you can do some things, of course, right. But in fact, it is Hamiltonian. So it is a classical realm of, but of course you would admit, not only it is a classical realm, it is also quite beautiful, right? You get to do this interaction of ellipses. And so what...
phase space is compact. This is important, right?
Yeah.
Phase space is not infinite.
Yeah, this is because you see, since the semi-major axis is fixed, good point, the remaining phase space is indeed compact, because your eccentricity goes from 0 to 1, and your orientations, of course, are bound to lie on the surface.
So temperature can be negative. So beta can be negative.
Yeah, right. So, wonderful. So that's why this thing is so interesting to us. So now let me briefly, can you tell me the time, please?
You still have, well, it's 4:06, so we finish at 1:30.
Okay, so I have like 25 minutes. Okay, good. So what should I tell you about here? I should tell you about this this funny thermodynamics that we are dealing with here. You can imagine, of course, that this is not a trivial thing to compute, right? Because I need to know interaction energy between ellipses. I have this huge configuration space because for each ellipse, I can change the eccentricity and all orientations, and I have many ellipses. So it is quite a computational nightmare to do all those things, but we managed to do it. As Yuri said, the temperature can now be negative and positive. We need to introduce the second temperature because we conserve angular momentum, of course, right? And there is one temperature per each conservation law. And we invented some crazy brute force Monte Carlo code, which actually handles arbitrary thermodynamic equilibrium. We found many beautiful things. But our main achievements, at least from my perspective of non-Gibbsian stuff, are the following. First, we were able to prove spontaneous symmetry breaking. No, this is not first, this is second. First, we were able to prove that TT thermodynamics breaks down at low enough temperatures. And then we also were able to show analytic proof. We gave an analytic proof of symmetry breaking. Now, to appreciate that these things are real achievements, the only way to appreciate it is to, you see, it's easy for me to tell you, oh, thermodynamics of ellipses. When you write down the corresponding nonlinear Poisson-Boltzmann equation which solves this thermodynamics, you get all these integrals over eccentricities, orientations. So only a good way to address this thing is this. Why Tremaine needs help from theorists? Tremaine from theorists. So Tremaine and Tuma and many others were working on this problem for quite a long time. And of course, he is a superb theoretician in galactic dynamics and stuff like that. So when we just started to work on this, I did not expect that we will meaningfully contribute. I was just curious about this ellipsis. So Levin said, this is a good problem. I was curious about this ellipsis, whatever. We didn't expect much, but actually we did, maybe because being newcomers, we saw something which was not done by Tremaine. So we did advance, I would say, this. We were not pioneers, but we did bring some beautiful mathematics here. So let me tell you about this beautiful mathematics. This breakdown of this thing, again, so one thing which I didn't realize, it was pointed out by Tremaine, it was that microcanonical thing still diverges for stellar systems. Another thing which I didn't recognize, and this was pointed out by Jiarong, our graduate student. So Tremaine things was pretty simple, but I didn't somehow. This thing is also pretty simple, but I didn't understand it somehow. But she pointed out the following. If you take an ellipse, among those ellipses, there are degenerate ellipses with eccentricity 1. So it is like a pencil, like a mass on a line. So this mass on a line diverges here because near the turning point. And so when we started thinking about it, I told Jiarong, look, I said, if I have two degenerate ellipses, since their masses are divergent here, they will like to stick together because it will be infinite energy. A few days later, she came back and said, this is really funny. So she came back and said, look, they will diverge even if they are like this. If you just take two masses on a line, the self-gravitating energy is still divergent. This is, of course, trivial, but somehow I didn't see it. Why is it trivial? Because if you have constant density on a line and another constant density on a line, then the energy here will be given by double integral dx1, dx2, 1 over modulus x1, x2, which of course diverges logarithmically. What's the problem? So if you take, therefore, two degenerate ellipses and put them on top of each other, okay, you get a divergence. And this divergence is logarithmic. It means, for example, that if your ellipses are not perfectly degenerate, there will be an energy of order log 1 over 1 minus eccentricity. Right? Eccentricity 1 fully degenerate. It also means that if they are degenerate but not exactly aligned with some angle here, theta, the energy will be logarithmic 1 over theta. This is what's the meaning of logarithmic divergence. And here comes the most interesting, again, to me at least, part of this talk. Now, most interesting will be non-Gibbs, but this is one of the interesting parts of this talk. It's this. For the sake of the argument, consider thermodynamics of rods, infinitely thin rods. If I put those rods at an angle theta between them, this will be unlikely, not too much phase space here. So by putting them at an angle theta, I am paying a penalty in phase space, which is theta squared. Okay? On the other hand, the Boltzmann factor here which is that's it. You have a critical temperature. If your inverse temperature is large, this thing will diverge. Large beta, negative power, diverges. So as you make the temperature of this cluster too small, okay, the ellipses will become degenerate and will lie right on top of each other. And for example, the fact that our numerical code reproduced this thing was one of the reasons that we believed in it. At small enough temperatures, it all collapses into this aligned degenerate ellipses. Another thing here, the same thing immediately gives you an analytic proof of symmetry breaking. Forget for a sec this statistical mechanics. Just consider all these ellipses. The fact that if I make all of them degenerate and put them right on top of each other, I will get arbitrarily large interaction energy. Okay? On the other hand, if my system is spherical, that is to say, if my overall potential is spherical, so I can have degenerate ellipses, but they have to be spherically symmetrically distributed. Or I can have circles, but they have to be spherically. It's easy mathematical exercise to show that if your ellipses are spherically symmetrically distributed in their orientations, the resulting energy is finite interaction energy, okay? If you put all of them spherically symmetrically, of course, you have spherically symmetrical potential with a finite energy. So that immediately gives you the analytic proof of the symmetry breaking. Since certain energies are not achievable for spherically symmetrical distributions, there must exist equilibria with broken symmetry, okay? That's simple, almost trivial, but we communicated this claim to fame to Scott Tremaine, and I think he appreciated it as a valid one. Do I remember correctly? So, so apparently those very simple considerations were not done before us. Even though I think he mostly appreciated the fact that we can solve the problem in full generality and can now perhaps try to how to say it, try to really model M31 and claim that it is thermodynamic equilibrium in the skies, okay? So in the remaining, whatever, 10 minutes, right, I will finish even earlier. Let me tell you this non-Gibbsian stuff, which I like so much. So you see, I don't have any problem with the fact that thermodynamics does not apply to normal self-gravitating system. By the way, you can ask, I think this is an important point where clarity would be useful. Cannot use, you would think, look, stars in elliptical orbits are still stars. So we should still apply normal thermodynamics to them. What's the problem that one of the stars is 10 to the power 8? Of course, formally you are right. So ultimately, after infinitely long time, the resulting equilibrium will be full equilibrium, which does not exist. It will evaporate, the usual stuff. But what we are doing, of course, is just an intermediate asymptotic, right? That is to say, on relatively reasonable time scales, I can treat ellipses as ellipses. I have forgotten to say this little thing. So, but now let me get to the most interesting part of this talk. So like I said, to normal gravitationally interacting point masses, I cannot apply thermodynamics, Gibbsian or non-Gibbsian, simply because those systems do not reach thermodynamic equilibrium. Right? A system not in equilibrium cannot be described by Gibbsian equilibrium. But here, you see, the situation is way more interesting. So let me show you one of the plots from our, come on, I remember it, I don't need to show it. Let me show you one of the plots from our paper. So this was non-rotating cluster, which is characterized only by one temperature beta, which can be negative or positive. And here I will plot the gravitational energy of interacting ellipses. Since it is negative, I take modulus. So this is gravitational interaction energy between ellipses. So we have found some solutions here. Doesn't matter how exactly it goes. So there are some solutions with small interaction energy, which is just spherically symmetrical solution. If you solve self-consistently the corresponding nonlinear Poisson-Boltzmann distribution, it's Poisson because I am solving for gravitational potential. It's Boltzmann because the density is given by the equilibrium density distribution in a given potential, okay? Normal thermodynamic thing. So Boltzmann-Poisson equation will always have spherically symmetrical solutions. Then, as we have discussed, since our ellipses can go degenerate and merge, there are solutions with infinite energy. Since our code was numerical, solutions with infinite energy were represented by some very large energy. So we literally see in our three projections just one stick. All stars go into the same orbit, okay? So we have found this branch, but then there is also this branch, corresponding to the symmetry-broken things, where the interaction energy is more than what a spherical system can do. What I find truly exciting about this problem is this fact, that at a certain temperature, I have a coexistence. That is to say, my numerical code finds two solutions simultaneously. One with all ellipses aligned, but at the same temperature, if I choose slightly different strategy for finding the solution, another thermodynamic equilibrium is found with a broken symmetry, but not the degenerate one. Now, let us think about it. What does it mean? What is the reason for existence of this upper branch with degenerate ellipses lying right on top of each other? The reason for existence of this thing is, of course, the divergence of the full statistical sum. Of course, you understand, this I calculate by solving mean field theory, right? I choose some mean field potential, and it is in this mean field potential where I distribute ellipses. Having distributed ellipses, I calculate the density. Knowing the density, I calculate the potential. I keep going until I converge. So I'm not really calculating the full statistical sum. I'm solving only the mean field theory with some temperature. There is this solution of the mean field theory and this solution of the mean field theory, without, beyond reasonable doubt, corresponds to the divergent statistical sum. Because of this infinite interacting energy and logarithmically divergent potential, statistical sum diverges. However, if my numerical code uses mean field theory, also with some temperature, so in a sense, what I'm doing is Boltzmann, but non-Gibbs, because statistical sum diverges. That is to say, it appears, yeah, I should calm down, because it was explained to me that the reason why Japanese and Chinese are so much better on coronavirus is because they speak calmly, okay? Right, but that's the problem. So yes, you see, the two solutions that we find here are.
But now people cannot hear you. Maybe.
Anyway, I'm near the finish, whatever, and I do testing at NYU, so I'm fine.
I'm far away. Yuri's safe. Josh is far away.
No, we're being tested at NYU, so we're safe. Anyway, so let me just finish. So the fact that this branch, this degenerate branch, exists at this inverse temperature means that my statistical sum diverges. The fact that this solution exists at the same time means that in the mean field theory sense, the broken symmetry state exists. So in some sense, these are real, okay? Those are equilibria. But those are not equilibria which I can find from the full statistical sum. These are non-Gibbsian equilibria. Statistical equilibrium. And this, in fact, is a real puzzle, I think. I will explain to you why is it a real puzzle. Of course, at the level of the mean field theory, what's the problem? You have some nonlinear equation. If you have a nonlinear equation, everybody knows it can have multiple solutions, right? All this hysteresis phenomena and stuff like that. But that's not my point. My point is that obviously to this ellipses, mean field theory will be applicable quite well because we are dealing with long-range forces. So this really is a good equilibrium. That is to say, I have zero doubt that if I had very powerful computer and if I put these ellipses into my computer, they will stay there. Moreover, to describe what they do, I will use some temperature. But if I want to be more precise, because you understand, in normal circumstances, full statistical sum gives you more accurate information than the mean field theory. So if I want to go beyond mean field theory, I destroy my statistical equilibrium. So apparently, these systems demonstrate quasi-equilibria or quasi-statistical or non-Gibbsian equilibria. And this is what really interests me here and what I plan to pursue. I want to understand what is this non-Gibbsian thing, like how should we describe? You understand, right? This is the last thing I wanted to say. It looks like it is verboten to go beyond mean field approximation to the full statistical description. So therefore, this is this precarious, whatever, equilibrium which cannot be described by normal Gibbs distribution. And that's what I find interesting, despite M37, extreme eccentricity in spirals, elliptical disks, and everything else. but we shall see. Okay, that's all I wanted to say.
I have the list. If people want to ask questions, raise your hand. I can look at that.
We can't hear you, David.
Just tell people if they have questions. If you have questions, just raise your hand. We can see who's raising your hand. And while you wait to do that, let me ask a question about, I think, a related system that also has this property, which is I have a galaxy, and it does not form a galaxy, but the galaxy is so massive that the two-body relaxation time is much longer than the age of the universe, which is a good description of a galaxy. It's a good description.
Which is true, in fact, right?
Whether I think about it as stars or dark matter. I think I also have this quasi-equilibrium, because violent relaxation drives a galaxy to a state where it tends to have, and we have no derivation of this. This is what it's a, we know that
I think I know what you're talking about, David. Violent relaxation, of course, is a well-known phenomenon.
Right.
You are actually operating in the so-called Vlasov regime. So in this regime where Vlasov theory should be used together with Poisson equation, it's called Vlasov-Poisson description. Indeed, there will be some relaxation, but this relaxation is only in the sense of hydrodynamic, only in the sense of kinetic instabilities in the system. That is to say, a certain large classes of potentials are excluded because they would lead to instabilities and to violent events. However, any system which is not unstable dynamically is a possible endpoint of your relaxation as a matter of principle. It's like a fluid, like, how to say it? I think it's a very important, because this is what other people were saying to me when I was talking non-Gibbsian, but this is very, very different, because you see, of course, if you have, for example, two-dimensional fluid, then in a two-dimensional fluid, for example, this is an example much simpler than you, this is a very good point. Very good point. In fact, so good I should have talked about it myself, because this is the important thing to understand, that what I do here is different. Take 2D Euler on infinite plane. 2D Euler on infinite plane has solutions where psi is the stream function such that vorticity, okay? That is to say, you can have lots of possible circular flows. Some of them will be unstable, and those will violently relax into another circular symmetrical system, which is not violently unstable, and there are lots and lots of those systems. Those are dynamical equilibria. They are not statistical equilibria. This is the difference, because here my ellipses are still interacting with each other. I am using, remember, both. In this case that you are referring to, your distribution here will not be Boltzmann. Your omega will not be equal. Right. It will be anything. Anything which is dynamically stable. But in my case, I do use temperature. This is the crazy part. I do use temperature. I do believe that it is those thermal distributions which get established. And yet, they are not thermal enough to use the total Gibbs distribution. This is what I find. Maybe I'm totally misguided, of course, but I did honestly try to talk to statistical, some first-class statistical people. They just wrote back to me saying, sorry, we cannot help you. Maybe it meant that whatever, you are so crazy now that you are beyond salvation or something, but who knows?
Yeah, I've tried to interest them even in just violent relaxation. And my experience with statistical physicists has not been, they were limited in their willingness to venture outside of what they've already been doing.
Right, right, maybe. Yeah, this violent relaxation, of course, it started, I think, with Lyndon Bell.
That's right.
I think Tremaine did a lot also on this violent relaxation. It is well known, in fact, in plasma physics, right? When we deal with collisionless systems, they often will undergo some violent relaxation, after which, however, what we reach is not Boltzmann, and so that's fine. What I have here, however, is Boltzmann, which is non-Gibbs.
But I want to comment.
Adam has a question, so let me turn to Adam.
Thanks. This is really interesting. So does this change, or how does this change if the central potential isn't 1 over r, right? If you don't get ellipses, can you do something similar if it's 1 over r squared or 1 over square root r or something?
Did the quality of sound is...
I understood.
You understood? Can you repeat it for me?
What happens if the potential is not 1 over r, but 1 over r squared or 1 over square root of r?
Ah, okay. So that's I think the margin here is logarithm. That's because the reason why I claim that logarithm is the margin is because we are looking whether or not there are these hidden funny corners in phase space, right? And then we are competing between this integral, that is to say, this is just the measure in phase space, right? This is a priori size.
I think Adam is asking something different. I think he's asking, what if the potential of the black hole, what of the central potential?
Oh, if you change the central part of the potential. Oh, if you change the central part of the potential, what will happen? This is, of course, I think in the first approximation, of course, your ellipses will start to precess, I would think, right? And then I think instead of your input as ellipses, you will get this, what do you call those things? Annuli, right? And then I think, in fact, at some point when we were thinking about it, I thought that I had a great achievement, that I realized that one can do statistical mechanics of annuli, only to later discover that Tremaine has done it many years ago. So indeed, right? I don't know. I think this guy is equally equipped to answer this question. So I think it will be first effect, ellipses become annuli, but then you can still get to do statistical mechanics of annuli. Moreover, it was done in some.
But you are not able to say anything about eccentricities. You only will be able to say about the orientation of orbital planes.
But will eccentricities change?
Not so quickly, but yes.
But then you are saying this annuli will change their radii. Okay, so but still you get some new funny configuration space which will work on different intermediate asymptotic time scale. Right. So there will be some kind of statistical mechanics of that system too. Right.
So a question from Will.
Well, it's really a follow-on. One of the key points, though, in the spontaneous symmetry breaking was that you had line distributions of masses, and that gave you the right potential.
Yes, yes. But I think this is important.
Right now you have annuli, and so you don't have line distribution of masses anymore. That doesn't happen in non-1 over r potentials, right?
Yes,
so
I think
you lose your spontaneous symmetry breaking?
Probably. Do you? I'm not sure. You certainly lose our proof of spontaneous symmetry breaking. Because remember, our proof of spontaneous symmetry breaking was very, very generous. I said there is infinity, and spherical symmetrical distributions only have a finite energy. Therefore, there must exist intermediate steps between infinity and you don't really need. So there are two questions, therefore, here. So I would think that because, as you correctly said, once I lose degenerate ellipses, I lose infinity. Therefore, the resulting thermodynamics will not have a breakdown temperature, right? So that is to say, at any temperature, your statistical sum will converge. But the fact that it converges does not prevent you from proving proving symmetry breaking in the following sense. If your spherically symmetrical distributions have small enough binding energy, and if you can point out to some funny distribution of your annuli which have a higher binding energy, here you have your symmetry breaking. So certainly I would think you can, if your annuli, for example, go into the same plane, probably there will be much larger interaction energy there. So I would expect that breakdown of symmetry from spherical to axisymmetric is to be expected, I would think, right? If I take this annuli and instead of arbitrarily orienting them in space, put them right on top of each other, the interaction energy will be larger. So in this limited sense, it will not be lopsided, but there will exist cylindrically symmetrical equilibria, which are not spherically symmetrical, I would think.
Right. Okay. Thank you.